Hello and welcome to this video tutorial. In this video, we're going to be looking at the lesson Weight of the Worlds. In this lesson, we're going to be distinguishing between mass and weight, how to calculate weight given the mass, how to calculate mass given the weight, and how to deal with the acceleration due to gravity on other worlds. Please remember to pause or rewind the video as you need to. Let's begin. Read along with me, please. On your next voyage to distant planets, you may determine the acceleration due to gravity by weighing standard masses as well as by dropping objects to check their acceleration. You have with you the following masses and weights originally marked on Earth. On Earth, g is 9.8 meters per second squared. Well, if you recall, when we updated our formula sheet, the weight of an object is equal to an object's mass times g. Now, in order to find the mass, we would need to divide by g. So to find the mass would be the weight divided by g. And also to find g, we would need to divide by mass. So we're going to take a look at these three relationships throughout this activity. Be prepared with your calculator to do the work along with us. Okay, so we are given mass A is a 1 kilogram mass. And we find that it weighs 9.8 newtons. Again, how did we get that? Well, weight would be 1.0 times g, which is 9.8 on Earth, which would give you, of course, 9.8. Okay, now for part B, C, and D, you can see we're given different things. So, for instance, I'm given mass of A, mass of C, but then for B and D, I'm given the weights and not the masses. So we're going to kind of be thinking opposite. We can use this equation right here. Where the mass, or excuse me, the weight would be equal to 1.0. And if I have the weight, I can figure out its mass. So the mass would be 1.0 divided by g, which is 9.8. So 1.0 divided by 9.8 is about 0.1. About 0.1. Okay, and again, I'm going to highlight all of the masses just so that we can keep track of them all. The first one is we're going to call this one mass A. This one we're going to call mass B. Now C, we're given the mass of C, but we got to find its weight. So weight on Earth would be 25 times 9.8. Multiply those two. And you should have been able to come up with about 245 newtons. Okay, and then finally, weight D. Given weight D, we can figure out the mass, right? It's going to be the weight divided by G, which would be 12 newtons divided by 9.8. So if we take 12 divided by 9.8, we get mass D, which is about 1.2 kilograms. Okay, I'm going to highlight that one too. So I'm highlighting all the masses to keep track of all the masses. And here's why. Let's write this down somewhere at the top. Weight is gravity, and gravity can change. From object to object. Bigger objects are going to have more gravitational pull than smaller objects. However, mass relates to the size of an object. Always stays the same. Mass will never change. The size of an object will never change. Okay, if we take a 120-pound person to the moon, that 120-pound person is going to have the exact same size, the same mass, but they will weigh 6 times less. They will weigh about 20 pounds as opposed to 120 pounds, but their mass will stay the same. Why is that helpful? Well, because we have mass A, mass B, mass C, and mass D, and we can label that all the way down through each one of these planets that's listed down here. So that's actually where we're going to start this exercise, is we're going to go through and we are going to identify all of those masses. We're going to copy them all down because the masses don't change. So mass C would be 25 kilograms. Mass D would be 1.2 kilograms. Okay, let me have those. I'm going to go ahead and highlight those ones as we go. Okay, so for the second planet, Regal 4, we know mass B is 0.10 kilograms. There we go, 0.10 kilograms. We know that mass C is 25 kilograms. We know mass D is 1.2 kilograms. So take a moment to just go ahead and do what I'm doing. Let's copy down those masses for every planet because they don't change from planet to planet. The size of the objects in kilograms do not change. Okay, so that part is completed. Now what we're going to do is we're going to work on some weight calculations. So the weight on Saturn is going to depend on the following. Remember, weight is equal to mg. Okay, that's our equation. That's our equation, right? Weight is equal to mg. But notice g is a little less on Saturn. So 9.1 meters per second squared as opposed to 9.8. So we're going to go mass, which in this case is 0.1, times 9.1, right? 9.1 is our new G on this particular planet, which would be Saturn. So let's go 0.1 times 9.1. And you get about 0.9 newtons. Okay, for weight C, we're going to go 25 kilograms times 9.1. And weight D, we're going to go 1.2 kilograms times 9.1. Okay, so 25 times 9.1 gives us about 228 newtons. And if we go 1.2 times 9.1, we get about 10.92 or about 11 newtons. Okay, now you'll notice in the next planet, Regal 4, we've got all the masses, we have the weight of object A, but what we don't have is we can't figure out the rest of the weights because we don't have G on this planet. Because remember, we have to go mass times G, and I don't know what G is yet. So we're going to have to figure that out first. So I'm kind of plugging in some stuff to kind of get ready for the calculation. we're going to go take that same mass, but times a different g. Now, how do you figure out g? Let's go back to the top. Remember, g, we can find that, the acceleration due to gravity, by taking the weight divided by the mass. So g is equal to the weight divided by the mass. So I do know the weight of A and the mass of A, and I'm going to use those two things to figure out what this is. So 25 newtons times, or divided by 1 kilogram, would be 25 meters per second squared. Okay, and now I feel pretty good about being able to finish the rest of the calculations, because that's going to be times 25, times 25, and times 25. Okay, so 0.1 times 25 would be about 2.5 newtons. Okay, 25 times 25 is 625 newtons. And 1.2 times 25 would be 30 newtons. Okay, now if we look at the planet, I guess Algon or Aljon, this we know all the masses and we know what the acceleration due to gravity is on this planet. So these are going to be some pretty easy weight calculations. Okay, weight, member is mg, so we're going to go 1.0 times, in this case, 4 meters per second squared, and that would give us 4 newtons. In the next one, we're going to go 0.1 times 4, which would be 0.4 newtons. Okay, and the next one, for weight C, we're going to go 25 kilograms times 4. Okay, some pretty easy mental math here. That's going to be 100 newtons. And weight D, we're going to go 1.2 times 4. Well, we know 12 times 4 is 48. That means 1.2 times 4 would be 4.8. Okay, and those are our weight calculations for A, B, C, and D on Algon or Aljon, however this is pronounced. Okay, and on our final planet, Takan 5, we have the masses there, and we have the weight calculated for object D. But again, once again, just like the second planet, we don't have the acceleration due to gravity G. So remember, G is found by taking the weight divided by the mass. So I'm going to take that known weight divided by that known mass, and I'm going to get G, which will end up being constant for all the other objects. So the weight is 48 newtons divided by 1.2 kilograms. Go ahead and divide those two. 48 divided by 1.2 gives us exactly 40 meters per second squared. So that's exactly how we're going to finish off these calculations here. We're going to go 1.0 times 40, which would be 40. And then we're going to go 0.1 times 40, which would be 4.0. And then lastly, we're going to go 25 times 40. Now, 25 times 4 would be 100. 25 times 40 would be 1,000, right? Or 100 times 10.